Welcome back to my course on discrete mathematics, and this is the second lecture of series of lectures that we are going to have on this online course. Well, the title is, Do you speak math? What does it mean? Are you curious about the title? Well, in mathematical terms, we do have many ways to express things, and we want to try to think mathematically, or in other words, it's a language of math. That's what I want to refer here. As we talk about this language of math, for example, if you say 2x plus 3, well, then all of a sudden an equation comes out. And what is this x? Well, let's see how this language of math works. Let's speak mathematically. Before going into it, I'll just want to give you this brief idea of mathematical habits. What is a mathematical habit? How do we view things mathematically? Make sense of problem and try to solve it. Just think about this. Suppose you are going out of your house and you find that it seems to be cloudy. What do you think? Maybe you try to calculate in your mind that what is the probability that today it might rain, and accordingly you make decisions. You take umbrella if needed. Yes, you are making sense of an issue ahead and you are trying to solve this issue. Moreover, mathematical reasoning. Yes, people often try to reason it out a logical way. Why? Why not? It's another questions that would help you in mathematical reasoning. Mathematical modeling of real world problems. Yes, for example, when you see like 5 roads connecting different parts of the city, and the city in itself is like a network of roads. Do you view it as a mathematical model in which you can have a graph? Well, when we talk about graph theory, we will go into this part and construct a viable argument. Whenever we talk about mathematical modeling or logics, we always come up with some argument. We always ask some questions. Yes, these arguments can give us or help us in making the right conclusions. Make use of inductions or structures if possible. Yes, we will talk about what is these inductions and structures. Later on we will see how these can be very useful for us in proving or disproving something. Recursive thinking, how a recursion or recursive principle or recursive functions can be useful for us. And finally, logics and proofs. So before we begin with this, I want to give you a very brief examples on how we can think mathematically. Let's say, for example, you have say 2x plus 3 equals x square. Now you might think about what is the value of x so that this equation becomes balanced. Well, you can think about the number that would fit you. Now think about another value. Say for example you have 3x plus 4 equals x square. Does the number fits this criteria? Well, 2x plus 3 maybe you can think about a number, a value of x can be 3. So that gives us 6 plus 3, that is 9, that equals 3 square, that is 9. How about 3x plus 4 equals x square? Again, you can think about a number, say for example 4. 3 times 4 is 12, 12 plus 4 is 16, and that equals 4 square. Yes. So whatever values that you have here, it's kind of repeats itself. So did you see some logics behind it? Did you see some relations developing? Did you see that you can come up with an argument? Did you see that we got a sense of this problem and we try to solve it with some mathematical reasoning? And did you see there is a recursion happening here, repeated again and again? It's kind of a recursive function coming up. Well, these are all the things that gives us the language of math. In fact, you are going to have mathematical habit. It's going to be habitual right now. Let's see more on how this can be done. So I'm going to show you some very brief concepts that you're going to see in depth later on. So today we are going to see very briefly what we are going to see in the days to come. So let's see, with the first part is the use of variables. So in the previous example we saw that say 2x plus 3 equals x square, where x is the variable, and as you went on to the next one, 3x plus 4 equals x square. So the variable, the value of x changed here. Yes, since the value is changing, we call it as a variable. So now the question is, are there numbers with a property that sum of their squares equals the square of their sums? So the first property you can think of. So you can take, for example, are there numbers a and b with property that a square plus b square equals a plus b the whole square? Or are there numbers a and b such that a square plus b square equals a plus b the whole square? Or do there exist any numbers a and b such that a square plus b square equals a plus b the whole square? Well, just to give an example, maybe you can think of numbers like a equals 1 and b equals 0. In that case, this is kind of solved, right? When a is 1, it becomes 1 square, plus b is 0, that is 0. So 1 square is 1 equals, on the right side, a plus b the whole square, so that's 1 plus 0 the whole square, that's again 1. So yeah, it is solved. So you can say that yes, there are numbers, or there exists a number a and b such that this equations can be solved. In other words, the variable that we talk about is the element that can change its value. So here are few points on the mathematical statements. Though we are going to see these things later on, let me just briefly tell what it is. A universal statement. A universal statement says that a certain property is true for all elements in a set. It's true for all the elements in the set. So for example, all positive numbers are greater than 0. Yeah, that's true, right? It's true for all the positive numbers. Then comes the next one, a conditional statement. A conditional statement says that if one thing is true, then some other thing also has to be true. For example, if 378 is divisible by 18, then 378 is divisible by 6. That is the condition. You can see there is a if then condition happening there. So that's why we call this as a conditional statement. So given a property that may or may not be true, that's what an extensional statement is. So extensional statement says that there is at least one thing for which the property is true. Yes, unlike the universal statement for which it is true for all the elements in set, but extensional statement, we are just worried about only one thing for which the property is true. So there is a prime number that is even. Yeah, you know that too. Yeah. So when it comes to universal statement, extensional statement, conditional statement, all these things we are going to see in depth in the coming lectures. So this is a very basic foundations for you to just understand what it means. Coming to the language of sets. Yes, as far as sets are concerned, well, again you might have studied in your high school about sets. So basically here is an example here, for example A. So there is set A, B and C. So values are given there for A, B and C. A is 1, 2 and 3, B is 3, 1 and 2, C is 1, 1, 2, 3, 3, 3. So the question is, what are the elements of A, B and C? How are A, B and C are related? So that's simple questions just to brush up your high school math. We know that A, B, C have exactly the same three elements, 1, 2 and 3. So therefore A, B and C are simply different way to represent the same set. When it comes to the second one, is the set that has a 0 element equals 0? As you can see here, the set which has 0, so that is a set with one element and the element is 0 in it, whereas 0 is just a symbol that represents the number 0. Yeah, there they can't be the same. That's one of the understanding that we have to get through when we talk about sets. How many elements are in the set 1, comma the set 1 brackets? Well, we know that from the set theory, this set has two elements. One is 1, the other one is the set whose only element is 1. Yeah, just to brush up the things that you learned in your high school. And set builder notation is given here. Let S denotes a set and let P of x be the property that elements of S may or may not satisfy. We may define a new set to be a set of all elements x in such that P of x is true. So we can denote that x, then the set of all elements of S such that this straight line indicates such that P of x. Yes. So this is a simple notation for us to understand. Later on we will be using that notations for us to represent the sets, and even in other parts to represent certain elements belong to a certain set. Language of relations. This is another thing that we are going to see later on in our course, but just to get an idea of this language of relations, say for example you have a set A which has 3 elements 0, 1 and 2. Then you have a set B, we have 1, 2 and 3. Let us say that an element x in A is related to an element y in B, if and only if x is less than y. So for this we can have a notation x or y. In other words, x is in relation with y, or in other words you can say in short form x is related to y. So we have this part. The condition is given to us as x is less than y. So in that case 0 is related to 1 since 0 is less than 1, 0 is related to 2 since 0 is less than 2, 0 is related to 3 since 0 is less than 3, 1 is related to 2 since 1 is less than 2, 1 is related to 3 since 1 is less than 3, and 2 is related to 3 since 2 is less than 3. On the other hand, if you have a notation like x or crossed y, in other words in short form we can tell it as x is not related to y, then you can represent like the following: 1 is not related to 1 because 1 is not less than 1, 2 is not related to 1 because 2 is not less than 1, and 2 is not related to 2 since 2 is not less than 1. So we can see, we can establish a relation between the elements. There are a lot of things with this similar thought which we will be covering on when we talk about the relation itself. Then comes the functions. Well, in most cases when we talk about functions, even in programming terms, we try to write a specific code to perform a specific task. In a similar way, the language of function in mathematical terms we can think as a mission. Suppose if f is a function from x to y and an input x of x is given, imagine f to be the machine that processes x in a certain way to produce the output f of x. Yes, you can think about x is given input and this function machine has to perform this task and it has to give f of x. Let's see how this is done. Let's talk about the function here. One of the function that we have in hand is the squaring function. F from R to R is defined by the formula f of x equals x square, that's x square, for all real numbers. So here the squaring function we have f of x equals x square for all real numbers x. So this means that no matter what real number input is substituted for x, the output of x will be square of that number. Suppose you are giving x as the input. This is to say that we have f of x equals x square. This is as if you are saying x is related to x square. In other words, x implies x square. We will talk about the implication operator later on. And moreover, you can think of any numbers, because the squaring function here with the definition saying that f of x equals x square for all real numbers x, for any number. So whatever number you give inside, when you get out, it is the square of its value. Say for example, let's consider your x as 3. So if f of 3, then that's going to be 3 square. Yes. So therefore, you are going to have 9 coming out. How about, for example, you have x as 9 inside. What would be the value outside? Yes, it's going to be 81. The ones going inside is squared and then it comes out. So in programming terms, we also write a specific task to be performed and it gives the output of that function. But here mathematical part is quite essential for us here as we deal with this function. It can be anything you can define accordingly. Okay, let's consider one more example here. A successor function. G from z to z is defined by the formula g of n equals n plus 1. So thus, no matter what integer is substituted for n, the output of g will be the number plus 1, right? That's what we have. Whatever you have here, we always have n plus 1 as the output. No matter what integer is substituted for n, the output of g will be the number plus 1. So you can see the square box here representing whatever it is there, you always have plus 1. Say for example, it can be anything, it can be gamma, it can be omega, it can be x, y, it can be any number, any integer, any real value, whatever it is. If it is 0.5, well, the output is going to be 1.5. In other words, G sends each integer n to n plus 1 or symbolically y. So you can see here the successor function, how it works is g of n or g here, n implies n plus 1, that is the deal. So you can think of an example here again. Say for example, your g of 3 equals 3 plus 1, that's 4. That is a successor function. Say for example, your n is any other value, say 0.25. If n is g of 0.25 equals 0.25 plus 1, 1.25. Yes, that's how it is dealt with. You have 2 here, well, we are going to have 3 here. 2 plus 1 is 3. That's how the successor function works. Okay, let's see more on one more aspect of the function. So that's about the constant function. So a constant function is the function h from q to z defined by the formula h of r equals 2 for all rational numbers r. This function sends each rational number r to 2. In other words, no matter what the input, the output is always going to be 2. Say for example your input is say 5, so your output going to be 2. So it's going to be constant function, a constant output. At times we do need such things to happen. We need a constant value to be outputted. So whatever values that you have in hand is kind of ignored, and you already defined a constant value that you want as your output. For example, it's a value that you have in mind, then that's the value it's going to be there. Finally, about this equality function. So we can define this as the relation r implies r, or for the function f, and we have a function g, also r implies r, by the following formula: f of x equals the absolute value of x for all x is an element of r, and g of x is the root of x square for all x which are element of r. Thus f equals g. Well, yes, because the absolute value of any real number equals the square root of its square. We can think of any numbers, right? Say for example, if x is -3, then the absolute value of x is going to be +3. How about the root of -x3? That's going to be that's going to be 3, yeah, root of -3 the whole square. Yes, therefore from this observation we can see that the function g and function f, they are equal. In other words, they call equality function. This is very interesting observation, because this absolute value and the square root of its square, they are same, and in fact you can also imply, or you can also represent the same thing in the hardware with this same similar representation. Yes, in this lectures we have seen some basics of what you are going to see in the lectures to come, and in fact you have started to have habits or habitual to the mathematical language. Yes, let's speak math. Thank you for joining this lecture, and I am looking forward to the next lecture. See you then.